We're so excited today because we just did a session on daily life in ancient Rome and learned about Mount Vesuvius and what the effects were of Mount Vesuvius. And then it just works out so
Ah,
beautifully that we're able to connect with you and learn about how and why volcanoes are formed. And I said to the students that they could go get two pieces of paper for when you, so that they can kind of reproduce those little experiments that you're going to be doing. So they might be ready
oh,
for that.
great.
It's okay if they can reproduce that later. There's Delore. Delore,
Sure.
we missed you. Caden, nice to meet you. That's great to see. Big group today, Darren. We have 20 families so far. Um,
Oh, wow.
I'm going to turn it over to you because I know you have a lot to share about living in the ring of fire.
Okay, and I just noticed my computer was not plugged into the internet. Give me one moment. This might help me operate a little faster. There we go. Much better. All right, welcome everyone to the Alaska Sea Life Center. My name is Darren, and our program today is called Living in the Ring of Fire. So we're going to be talking about what the Ring of Fire is and connecting that to Mount Vesuvius, which you guys were just studying, it sounds like. Although I don't know a whole lot about that mountain. I have visited near there to the village of Pompeii when I was younger, probably when I was about 10 years old. And so I have a distant memory of seeing the village that was just completely sort of frozen in place by all the ash that just rained down on that village from that eruption. So super cool connection there. And so we're going to start off with a little bit about where I am here at the Alaska Sea Life Center. First, I would like to share with you our physical location. And here we are on the map. We're right in what's called South Central Alaska on the Gulf of Alaska here, the Pacific Ocean. This is a photo of our town. There's the Sea Life Center, and there is the ocean. So from where I'm standing, I could toss a rock into the ocean right now if I were outside. We're just that close. And being that close allows us to do a great job of taking care of Alaska's ocean animals. So we have animals here for folks to visit with. We have our seals and our stellar sea lions. These are the biggest sea lions in the world. They get to be a little over 2,000 pounds. And we have diving seabirds. So we've got puffins, guillemots, murres, auklets, and sea ducks. Pretty amazing. And then, of course, we've got tons and tons of fish and invertebrates, those animals without backbones like sea stars, anemones, crabs, urchins, cucumbers, chitons. We have a touch pool where visitors get to put their hands into the freezing cold water and see what those animals feel like when you touch them. That's super fun. We do sleepovers with kids like yourselves. They get to spend the night. They sleep right on the floor and then do some classroom programs in the evening before bedtime. And we also have a wildlife response program. What that is we rescue and rehabilitate stranded marine mammals from all over the state of Alaska. We also respond to ones that have already died, and we want to learn about those animals and learn why did they die, what's going on out there in the ocean. The other way that we learn about these animals is through research. So we have a team of scientists here at the Alaska Sea Life Center, and those scientists use all sorts of different tools and techniques to study Alaska's oceans and the animals that live out there. And that is one of the ways that we help animals out there in the ocean is by learning about them. Sometimes we have to get kind of hands-on, and there's one of our divers heading down for a scientific dive. This particular dive was for collection purposes to add new animals to our collection here at the Alaska Sea Life Center. And that is another way that we help animals by teaching people about them. So we want to have animals here so that we can teach people more about how those animals live out there in the wild. And this is looking right out the back door. Someone asked about the weather here today. It pretty much looks like that. It is a gorgeous day here in our town, and we're loving it. Probably for a lot of you guys, it's about the same, especially up in northern Canada. You get used to all the cold throughout the winter, and then when it finally starts to warm up again, it's really not that warm outside. It was frosty this morning, but going outside, it feels like a summer day suddenly, even though it's only about, maybe 10 degrees Celsius out there. It feels like you just want to go down to a short and t-shirts and just hang out on the deck. We love this time of year, especially when we get some nice sunshine like that. So that's a little bit about where we are. Now we are also on the edge of the Ring of Fire. So I'm working on getting joined into the WebEx meeting, so hopefully I can see your responses in a moment here. My computer is really not cooperating, but I think I've got it. Not connected to audio. There we go. All right, so I should be able to see the chat now. I would like you folks to tell me, what is the Ring of Fire? What do you think we're talking about when we say the Ring of Fire? Johnny Cash song, a ring that you would wear on your finger after it sat out in the sun too long. What is the Ring of Fire? So put that into the chat window. Johnny Cash song. Yes, Molly, you're right. We've got volcanoes. Something from the circus. Excellent. Actually, the circus came to town here one time, and I'm trying to remember, did they have a Ring of Fire? I think they did, actually, have a Ring of Fire. They shot someone out of a cannon through a circle of flames. Wait a minute. Kerrigan says volcanoes around the Pacific Rim. That is for sure the answer that I was looking for. Those of you who aren't familiar yet with the Ring of Fire, when we're talking geologically speaking, let's take a look at what that is and what that means here. So the Ring of Fire is this sort of line of volcanoes. So all of these little red triangles around the edge of the Pacific Ocean are volcanoes. Those are active volcanoes. There are over 450 of them, and that represents about 3/4 of the active volcanoes in the whole world. So most of the world's active volcanoes are found along this tiny little strip right around the edge of the Pacific Ocean, the Pacific Rim. My next question then is why? Why are most of the volcanoes in the world found right along that tiny little line? If you go back to the picture, truth be told, this doesn't look like a ring at all, but it's like an upside down horseshoe. That doesn't sound nearly as cool as the Ring of Fire. So imagine a whole circle, but that's where it gets its name. Why are there so many volcanoes there? Oh, and Mally just pointed out in the resource page that picture is uploaded. Tectonic plates. All right, so then my next question, plates shifting. All right, my next question, I have a feeling some of you already are familiar with this, at least somewhat, is what are tectonic plates? So here we have the just general makeup of the Earth, the layers of the Earth. Deep down inside, we've got a metallic core layer. If you think of like a hard-boiled egg, this would be the yolk. So there's that little circular component deep inside the Earth. And this is actually the source of most of the heat from within the Earth that melts this layer next to it, the mantle, which is a layer of liquid rock mostly, until you get to the very outer edge, and this would be like the eggshell, the crust. So the crust is where we live, and it's only just the very, very outer surface of our planet, where we've got solid rock. And then, of course, on some of that solid rock, there is ocean water or lakes sitting on top of the rock, but there is this solid layer of rock. But think about it, we're just basically living on an eggshell on the outside of this planet. The rest of it, underneath that, is very, very liquid rock. Although it's liquid rock, so it's not like swishing around like water, it does move and it can move. And so scientists have a theory that the crust, our little eggshell, is broken up into pieces. And this is what they think that looks like. All these black lines are the outlines of what we call tectonic plates. And the plates are big slabs of rock, but because they're floating on the mantle, they move around. And it takes millions of years or tens of millions of years for that to happen. But as those plates shift around, they crash into each other, they spread apart from each other, or they slide past each other. And that's what we're going to look at today, is what we call the plate boundaries. There are three main types of plate boundaries, the three that I just described. Those are convergent, divergent, and transform boundaries. And we're going to look at all three of those and see how scientists have put together this theory of plate tectonics using evidence from underneath the ocean, especially. So we're going to start with boundary A. And, oh, let's see, here we go. Boundary A. And I see that's how earthquakes happen when the plates crash into each other. That is one way that earthquakes happen. Really, any time one of these plates moves, it is an earthquake. That's basically the definition of an earthquake, is the movement of that crust layer. So all three of these types of plate boundaries would create earthquakes. But what we're going to look at is they're not all the same, for sure. So we're going to start with boundary A. Let's zoom in on that. And these three different types of boundaries are going to be either convergent, where they're smashing together, divergent, where they're spreading apart, or transform, where they're sliding past each other. So looking at boundary A here, is that convergent, divergent, or transform? What do you think? Boundary A. Are we converging, coming together, diverging, spreading apart, or is it a transform boundary where they're sliding past each other? I see DIV. All right, divergent. Very good. That's a tricky one to spell without me writing it in front of you. Oh. I'm going to go divergent, and then I'm going to hunt for another marker. Somehow these markers have disappeared inside our cart. Give me a moment. Let's see if I can find the real markers that actually work. Well, okay, let's try that again. Divergent. So I'm going to show you a model of a divergent boundary, and we're going to imagine that this divergent boundary is underneath the ocean. While I'm prepping my model, enjoy the stellar sea lion in his habitat. That's Pilot, the big guy, who's been cruising around behind me there. And so I want you to think about what will happen at this divergent boundary. So we've got these tectonic plates, these big slabs of rock floating on the mantle layer, and they are going to slide apart. At the bottom of the ocean is where this is going to happen. And we want to know what sort of feature is going to be created there at the bottom of the ocean when these two plates spread apart. All right, give me just a moment here. This involves shaving cream, so there's a little prep work.
Oh, George says a trench is going to happen.
Ah, all right. So a trench, that's one thought. Let me know if you got any other hypotheses of what is going to be created there at our divergent boundary. And then we'll see what the model predicts.
And Kira says an earthquake, and Maria says a valley.
Okay, so definitely there's going to be earthquakes because anytime, again, these plates move, there are earthquakes. All right, so I've got my two plates, and the two plates are going to spread apart. Now, all along here, this is my fault, along the divergent boundary. Remember that these big slabs of rock are sitting on top of that mantle layer. They're floating, and the mantle is under a lot of pressure. So as these two plates spread apart, the mantle pressure actually forces upwards, and the crust starts to lift up along that edge. And so what is actually created is a mountain range all along that whole plate boundary. And this right here is called a mid-ocean ridge. Let me get the focus a little bit better on there. Oop. Zero it in there, camera. There we go. This is called a mid-ocean ridge. And these were sort of the key to the theory of plate tectonics when they were developing this idea. Scientists did not know that these mountain ranges existed on the seafloor until about the 1950s and 60s. And this was after World War II. A lot of deep sea exploration technology was developed during that war to aid in submarine navigation. And after the war was over, humans used it for good. And they were able to survey the seafloor better than they ever had before and found these huge mountain ranges, tens of thousands of miles long on the seafloor. So these are huge things, and they're very long. And so this is called a mid-ocean ridge. And this, again, was one of the keys to the theory of plate tectonics really coming together. Because, as we'll see on the map in a minute, these ridges go all the way around the planet. And scientists had to get a little bit techie to really understand what was happening there. We'll talk a little bit about that. And it's an area for further research if you're super curious about this. But right now, I like to draw pictures. So I'm going to draw a picture of a mid-ocean ridge here on my page. So if you have this document, print it out for yourself or even digitally. You could spend some time doing a little picture. You just basically draw a little bump over the crack there at each end. And then you can draw some little squiggly lines to show that that hill goes upwards and then continues on over the other side. And that right there is our mid-ocean ridge. And this, again, is formed because of all that sort of pressure pushing up from the mantle. As those two plates spread apart, some of this liquid rock is going to get shoved upwards by that pressure. And it's basically like if you imagine one volcano, but all along this whole line. That's kind of the idea there, as it keeps just sort of pushing up the edges of those new rocks as they're formed. So as these plates spread apart, new crust is being formed right there at that divergent boundary. And so in order to find this, again, scientists had to get better at exploring the deep sea, the ocean floor. So that's what we're going to look at now, is the ocean floor. Lucky for us, scientists now have a much better map of the ocean floor. This one is even from a few years back. We've got better and better mapping tools, It seems like every year we're getting even better at exploring the sea floor. But this is a challenging place to explore, so we're still working on it. The ocean is huge, and we can't just see it down there, so we have to find creative ways to explore our ocean. But what we're looking for here and is a mid-ocean ridge. And I see someone had to step away and you just came back. Emily, to get you caught up, give me 1 second here. We are looking for evidence that scientists found of where two tectonic plates are spreading apart, because those two plates kind of lift up at the edges as they're spreading apart from this pressure underneath, and it creates this really long mountain range. And so we're under the sea, and we're looking for long, continuous mountain ranges on the sea floor. Now, in order to find these, what we're going to be looking for is, man, I'm really having a hard time with the glare this morning. Hold on a second. Nope. Give me 1 moment here. I'll try to adjust my brightness levels. That looks a little better. Mally, let me know if that is not showing up well. It looks a little better on my screen. But...
That's better than it was, yeah.
Okay, great. My little spotlight is giving me trouble. Oh, that's even better. Look at that.
Yeah, that was better. Just if you...
Sweet.
Yeah.
Okay, so if we look into the ocean, you see these darker areas. That's really deep water. And then, for example, up here in the Bering Sea between Alaska and Russia, it's very, very shallow. That's for that's what the light blue shows. This is very shallow water. This is where walruses and gray whales, eider ducks are able to dive down and feed on the sea floor, because it's only about 100 meters deep for this huge area of the Bering Sea. This is part of the continental shelf. That's why there's so much food out there in the Bering Sea. One of the reasons is because of all that shallow area. It's very, very productive. So dark blue is deep water, light blue is shallow water. So what we're looking for is long lines of light blue where there's sort of a lifted up area of the ocean. Now you might look at this one here, but if we look really closely at that, it's actually tiny separate little mountains. And so that is not a mid-ocean ridge. We'll come back to that. But it is not a mid-ocean ridge. We're looking for something that is a continuous feature all the way through the ocean. So I'm going to point out one of these mid-ocean ridges, and then I want you to tell me where you see others. So there's one that starts right here and goes right down to that spot and then connects over this way. Where else in the world do you see ridges like that? So if I pull my lines away, they're these kind of light blue fuzzy lines. Where else do you see those light blue fuzzy lines out there in the ocean? In the middle of the Atlantic Ocean, exactly. So right up through the middle of the Atlantic is called the Atlantic Mid-Ocean Ridge. And this one it actually goes right through Iceland. This one is evidence that the Atlantic Ocean is growing. It's a fairly new ocean. It's still pretty small, but it's getting bigger as those plates spread apart. And this is the longest single mid-ocean ridge. Off to this side. So which side are we looking at? Left side or right side? From, it looks like Kyra. The left. All right. Starting all the way over on the left side, we have a mid-ocean ridge that goes just like this. And it actually connects right up to the one that I drew before. How about on the right side? Is there another one? Yep. That's actually a continuation of the one that goes off the left side of the map, because the globe, the Earth is round, right? So it just keeps on going. That one heads up into the Red Sea. right there. And there is a connecting one right down here just above Antarctica that loops up to that one. So those are all of the major mid-ocean ridges. And the next part is a little bit complicated, so I'm just going to kind of touch on it. Again, this is an area for, yep, right there by Argentina. Oh, little tiny thing. I'm actually not sure exactly what that is right there against South America, but this one right here next to Argentina for sure is one of them. So the way that scientists really decided that this was what was truly happening is they looked at those mid-ocean ridges and they drilled into the seafloor on both sides of these huge mountain ranges. And what they found was the rocks, the same distance from that middle point. The rocks had very similar properties. And what they could look at is the magnetic properties of those rocks, because in time, the liquid rock that's sort of drifting around the mantle will always be pointed toward magnetic North Pole. And when those rocks turn solid, they're sort of frozen in time. So the magnetic properties of these rocks out here matched. And every once in a while, that's what's called magnetic striping. If you look that up, they could see that if you went the same distance on both sides of these ridges, the magnetic properties would be exactly the same, but those properties change over time. So those stripes just went out from these middle ridges. And that was really strong evidence that the rock is indeed just pressing and moving outward from that central location. So mid-ocean ridges were the real key to launching this theory of plate tectonics. Remember, I said that only started back in the 1950s and 60s. This is a pretty new theory in the grand scheme of things, especially for something so big as far as how we understand the planet that we live on and how these huge mountain ranges are created. This is pretty new thinking, but the evidence is so great down there under the ocean that scientists have developed this theory that's incredibly well accepted at this point. So going back to our tectonic plates now, I want to look at the Pacific plate, and we're looking at this edge right here. All along that edge, if we say that that's a divergent boundary, then that would mean that the plate is moving away from that point, right? But it kind of bends around the corner. So if we just take an average of all those, we might guess or hypothesize, scientifically speaking, that the plate, this Pacific plate, which is this big chunk here, is moving to the northwest. So that's a good start. Now with science, as we start to answer some questions, we develop new questions. And I see Mally has come up with a question of her own. I wonder if that's because technology and satellites are much better. It's interesting, but we do use satellites to study the ocean floor. And like I said before, it's challenging to study the ocean floor, and so we keep getting more and more creative. And one of the ways that we've gotten creative, scientists have gotten creative, is finding ways to look at the Earth from space and interpret from the surface of the ocean what they can understand about the bottom of the ocean. We're getting better at that. So of course, in the early days, sonar would have been the main way to study the ocean floor, but nowadays they are combining that with information from satellites. And so indeed, technology, satellites, computing power, all of those things together are helping us to develop a better understanding of what's going on the ocean floor. So we've got one boundary down, the divergent boundary, and now we're going to move on to boundary B. We're going to have two plates colliding together, and so that's the opposite of divergent. It's going to be convergent, where these two things are coming together. And again, we're going to be looking at the ocean floor, but this time we're going to look at the edge between the ocean and the continent. So between the edge, or the edge between the ocean and the land, we're going to have two pieces of crust. And it's going to be a convergent boundary between them. And I want to know when those two plates come together, what is going to happen? So first, we're going to be watching this from the edge here. And I'm going to brighten it up just a little because it's fairly dark now. And we're going to focus right about there. There we go. All right. So now I have my two plates coming together. And as these two plates press into each other, the green one you can see sticks up a little higher than the white one. And that means the green one is my continent because the land, the rock, is higher than the land at the bottom of the ocean. So here we've got the ocean, there's the continent. And as these two push together, you can see the continent is kind of riding up over the top of the bottom of the sea floor. That's not just because it sticks up higher. Remember, both of these pieces of crust are floating on the same liquid, the same mantle layer. And the reason why the continental crust is going to go up a little higher is because it's a lighter type of rock. It tends to be made of granite, where the sea floor is made of something called basalt, which is a more dense, a heavier type of rock. And so as these two plates crash together, a couple things happen. You can see along here, the continent is kind of bending and buckling. So we're creating some mountains. Now this time, instead of a long, smooth mid-ocean ridge, we're going to make these big broken pieces, very, very high, sharp, jagged mountains at this convergent boundary because of this kind of crushing act. And right here at the edge, I want you to watch this piece of the foot of the mountain there. As these two come together, watch what happens there. See how that toe of the continent kind of kicked out into the ocean? When that happens, it's going to move a whole lot of water all at once. And when you move a whole lot of water out there in the ocean all at once, what natural disaster can result from that? Who could tell me in the chat? What natural disaster could happen as a result of this? A tsunami. Very good, Charlotte. All right, so as these two plates come together, we're creating all these huge mountains. We can create things like tsunamis out here on the ocean side, and the continent is going to ride up on top of the ocean floor. And as that happens then, if we sort of zoom in and imagine we're down under the ocean floor is going to create a feature that looks like this. So for those of you who expected a valley before, this is where we're going to create our valley at the divergent, or the convergent boundary, sorry. We're going to create this deep, 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 deep valley at the bottom of the ocean. And these are the deepest places in the ocean. This is called a deep ocean trench. So a deep ocean trench is going to be our clue that we have found a convergent boundary. So let's go back to our, actually, I'm going to draw a picture again for my convergent boundary. Let me get my camera back together. For my convergent boundary, I've got this heavy, dense ocean floor riding on top, or riding underneath the continent. We're going to create some mountains. Some of them will be volcanic because as things get broken up, there will be extra pressure down there in the mantle pushing up through these and in some spots it's actually going to push up through as volcanoes. And I would have to look if Mount Vesuvius is on the edge of convergent boundary, if that's why the volcano is there or not. I don't know for sure on that one. But as that sea floor dives down, it creates this deep ocean trench. So that's the feature. That's going to help scientists understand that there is a convergent boundary.
Just Darren, can I ask a question? Just wondering how long are those pieces moving all the time, or do they suddenly start moving, and how fast do they move?
Those are all questions that will be answered through the course of the program today, Mally.
I'm just so excited to see that. Okay.
It varies. So what we'll see is in some areas there are little tiny movements kind of all the time, but sometimes those plates might get kind of caught up with each other. You can imagine, not exactly smooth edges of these things. They're all just rock, right? And so they'll get caught together, build up a lot of energy, a lot of pressure as things are getting forced along, and then they might release a whole bunch at once. That's when we have more of a massive earthquake. And so there are periods of small activity kind of all the time, punctuated by periods of much bigger forces being released. And then as far as the speed, I'll show you a way that we can look at the speed of these plates. We'll actually calculate it together. And that's probably going to vary also for different plates. I've only looked at one of them. So by the end of the program, we will have one example of how fast these plates are moving, or at least an average for the last 30 million years or so. All right. So let's go back to our map then that we started before. And now we're looking for convergent boundaries. So areas where the ocean is very, very, very deep. And in this case, where the divergent boundary was spreading apart, creating this kind of broad hump of a mountain range, we're creating such a narrow trench as those two plates are kind of continually squishing together. We're going to create a very, very narrow feature that is extremely deep. And I'm going to grab a different color here. So I'm going to zoom in on one example of a deep ocean trench that is here along the west coast of South America, all the way down right there. That's super funny. This is a red marker, but on the screen it shows a blue. I don't know if it looks red to you guys. It looks red to me. It's not a very deep color. All right, so right along there, let me pull my line away for a second. You can see that super dark blue line just right at the edge of the continent. And so this is what we were looking at here. And you can notice on the continent there, we've got the Andes Mountains. These are some of the very high mountains of the world all along there. All that bright red is extremely high mountains. And they're also very narrow, where they've been just kind of smashed together. So imagine these things are just crushing each other, and those mountains are getting forced up right at the edge at the same time that the ocean floor is getting forced downward. That's a process called subduction that's creating that trench. Those of you who are in the upper grade levels, subduction zones are those places where you're going to find a convergent boundary. So let me zoom out just a bit here and look around. Do you see where else do we have those convergent boundaries, those deep ocean trenches? Besides this one here that I drew, where else do we see those on the map? see, Sigrid says Vesuvius was caused by convergent movement. That would have been my guess, but I would have to really take some time to look that up to see exactly what's going on there. I can't even remember what period of time we were talking about. So does anybody see any other trenches, those deep dark blue lines, besides this one on the west coast of South America? Anywhere else? On the left, yes, here we go. To the left side again. Over here, coming up from New Zealand. Here's one. Right along that edge. Toward Papua New Guinea. Up through Micronesia. On to the very left edge. To the Indian Ocean. And then right up through here. All around this way. And if you keep following these lines, they just keep on going right up Eastern Asia. Like you said, all the way up to Russia. This is the Kamchatka Peninsula. That's the Kuril Trench right alongside there. And then we have another one that connects from Alaska, the Aleutian Trench. Sort of smiley face one. There is another one here along Central America. Small one. And there's one down here that has a funny name off the tip of South America to the southeast. That's called the South Sandwich Trench. But that's most of them. Now this one over here in the Indian Ocean connects on the other side again. My map moved. So there's a little more of that one right there. But that's most of the trenches of the world. And if we compare that to our map that we looked at originally with the Ring of Fire, look at how many of those match up with that image of the Ring of Fire. Up the west coast of South America, tons of volcanoes. Central America, tons. Up here, it's kind of sparse again, but there's tons through here, a whole bunch down this way, all down here, over into the Indian Ocean, along that line through Micronesia and down to New Zealand. So that line of volcanoes, the Ring of Fire, actually follows very closely with our map that we now have of those deep ocean trenches. So these deep ocean trenches were another clue to this movement of tectonic plates around the world. So if I go back to my layer with the actual plates outlined, now if we imagine, if our hypothesis is true, and the Pacific plate is moving to the northwest, then this would be convergent right there. Convergent, 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 convergent. So that all works except for right here is moving a different direction. That could be just because of the way that these two plates interact, but there's a trench created there. So it's not that the piece of the plate is like turning the corner somehow, but there's something going on there that's a little unusual. But for the most part, all of our evidence right here is suggesting that that Pacific plate is moving to the northwest, which means then that right here, this would be our third type of plate boundary, a transform boundary, right along the west coast of the United States. And here's where we talk about how much these plates move. Because if we're living, say, in California, and California, let's say, is just standing still, but the Pacific Ocean is sliding by, how would we know that? Earthquakes. Very good, Charlotte. So, are there lots of earthquakes in California? Absolutely. Let's take a look at a map that shows how many earthquakes there were in California for a certain period of time. So if we zoom in here, this map shows approximately They're all over the top of each other, but about 200 earthquakes. And this is 1 week in California. But all of these squares are very, very small, and these amount to 1 or 2 on the Richter scale, which is a measure of the strength of an earthquake, how much energy is released from the earthquake. So these are all very tiny. None of these would have been felt by humans. These were detected by scientific instruments, but there's tons of them all the time, hundreds and hundreds. And now we have even more sensitive scientific instruments that tell us even more frequently there are little tiny movements. So this is where the plates are just sort of sliding gradually by, a little bit at a time. A little bit at a time. What if there was a big one? If they got stuck together for a while and a lot of energy built up and they were kind of caught, kind of hung up, and then boom, all of a sudden there was a huge movement. That's when we have massive destruction in areas like California or anywhere. So this was 1 week in California. Then this map was printed Tuesday, December 4th, 2012. So this was a little while back now. The reason why I printed this map was because this had just happened in our office. We are, let's see, we're probably about 150 miles maybe from that big red square, the center of it. And our office one afternoon was just doing this. And I noticed some of you said you slept through an earthquake. When it just rocks gently like this, it's pretty easy to sleep through. But every once in a while we get one that's just like this. That's a little weird. It's very short. Might be kind of startling, but you might not know exactly what happened. Then sometimes we get earthquakes that are more like this. These are more obvious. When the whole place is shaking very rapidly and a lot like that, that's harder to sleep through. It kind of feels like you're riding a train suddenly, and it's a little more startling. So looking here at this week in Alaska, the same week we just looked at in California, look at the size of the squares here. California, they were all little tiny movements. And in Alaska, 3 of these were huge, over 5 on the Richter scale. Now it doesn't really qualify as a massive earthquake, it's just a large one. Yeah, sleeping through a 6.2. That's impressive. My kids have slept through, one of my kids has slept through a 7.1. The other one woke up terrified, and the cat was really scared. But one of our kids slept right through it and had no idea it happened. So in 1 week, we had 3 over 5 on the Richter scale and a whole bunch that were in the 3 and 4 range. Still hundreds of them. But this is a convergent boundary. So all of that energy that's coming together, being smashed into these 2 plates, has to go somewhere. And so that energy is released in those earthquakes. There's also a lot of volcanic activity. All these islands along here, many of them have volcanoes on them. So that's the difference here between a convergent and a transform boundary. At a divergent boundary, we would see similar, lots and lots of earthquakes, but not quite so powerful. So the convergent boundaries are the sources of the largest earthquakes that we have on the planet. They are also the reason for the Ring of Fire. That is the main reason why most of the world's volcanoes are right along there, is all of those convergent boundaries, because so much energy is being packed in there and released. I see a great question. How do we have earthquakes far away from plates sliding, like in Ontario? That is a little bit beyond my personal knowledge, but I can tell you it's far more complicated than what I'm presenting here. So there can be earthquakes way out here in the middle of the plate, and it could be related to volcanic activity. So there are places where the mantle is just extra hot, and that's what we're going to talk about next here when we talk about the speed of these plates moving around. And so that could impact it. Another part of it is when plates collide, that energy gets translated almost like a wave through the plate. And so you can get energy that gets transferred way out here, 1,000 miles away, if it's a strong enough impact, or not necessarily thinking of an impact, but a strong enough force between those two, some of that force gets translated to another point somewhere else in the plate where there might be a weak spot and the ability to move separately from pieces around it. So if you imagine this just big block, if I push on one end of a block of wood, the whole thing is feeling the force. And if there's a crack somewhere, that crack in the wood is going to be the place where something moves. So as those plates push together, there can be earthquakes far away from where the actual meeting of those plates is happening, but it may not be directly related, but it is a result of that force of those two coming together. So it is far more complicated. If we look at Alaska again, and I said earlier, we have far more sensitive instruments now. This is a more recent map of earthquakes in Alaska. This one shows 2 weeks now. And this one we printed after we had a 7.9 out here. And you can see it wasn't just one single earthquake. There was one massive one, 7.9, followed by a series of 4s almost immediately. And so there's this huge cluster over the course of a few weeks. There's going to be dozens or hundreds even with all the aftershocks. And that's where most of the energy was being released in this particular event. But all along at the same time, all those little tiny ones along that convergent boundary were happening. And as a result of all that activity, there are sort of waves of other earthquakes all throughout Alaska that are just being, that's the forces being kind of translated out into those areas. So this is not super far in the grand scheme of things, but that's about 1,000 miles from the plate boundary. So pretty far away. Whoa is right. All right. So the last thing I want to show is looking into the middle of a plate. Back to those volcanoes I showed you earlier. This is, here we have the islands of Hawaii. And they are part of a string of volcanoes that stretches thousands of miles off into the ocean. And it's a pretty straight line there for a while until it turns into another kind of straight line that just bends up off that way. But if we look really closely, those are all individual little volcanoes. And the only ones that are forming islands are these ones down here at the southeast end. That's because they are the newest volcanoes in this line. All of these over here are just older and older and older and older. So the way scientists interpret this is, give me a second for another model here. Something called the hotspot theory, where there is an area of the mantle, like I was saying a little bit ago, that's extra hot. And that's going to be right here. Every once in a while, that place will be active and a volcano will erupt. But the plate moves over the top of that hotspot, and the hotspot doesn't really move, or might only move just a little bit, not nearly as much as the plate itself. So as the plate moves, it's creating a map of where it's been through the course of these other volcanoes. It's creating a chain of what we call seamounts, undersea volcanoes, or if they break the surface, islands. And if you look at them from the side, there's this long line of volcanoes. But the newest one, the most recent one that I created, was this one way out here. And this one over here was the oldest. How did scientists figure that out? They went down and drilled in, and they can estimate the ages of these rocks, and they will find that these were the most recently created ones, and they get older and older and older and older. That can help them see not only which direction plates are moving, but how fast as well. So here in the Gulf of Alaska, we have some of these seamounts. And scientists have drilled down and estimated the ages of these rocks in these seamounts. And so here we have the axial seamount right at the Cobb hotspot. 0 MA indicates that these rocks are 0 million years old. Out here at the Warwick seamount, the rocks were 10 million years old, 20 million years old here, and all the way out at the Murray seamount, the rocks were 30 million years old. So as the plate has been moving to the northwest, like we suggested earlier, these rocks that were created here, or these mountains that were created here, went this direction. After 10 million years, they got this far. After 20 million years, they've gotten this far. And after 30 million years, they've gotten this far. So what we can do is estimate the speed that this plate has been traveling from the 30 million year old rocks to the brand new ones, which is the spot where those rocks were originally formed, became solid. It's 1,700 kilometers. In order to calculate the speed, then, all we have to do is take kilometers and divide it by years. So we have 1,700 kilometers, and it took 30 million years to go that far. I can cancel one of the zeros. For those of you who do that kind of math, we get to 170 divided by 3. Divide that out. We get that the plate has been traveling about 57 kilometers per million years, but that's not typically how we record speeds, right? So that comes down to about 5.7 centimeters per year. So Mally, you asked how fast do they go? For the last 30 million years, on average, the Pacific plate has been traveling about 5.7 centimeters per year. And, you know, if your bed moved over 6 centimeters a year, that would be really weird, right? But that's not how it works. The Earth, or the crust that we're living on, is just where we are, and we don't notice the movement except in those cases of earthquakes. We might actually feel it, but we don't generally see ourselves sliding across the planet. We don't notice that the Pacific Ocean is a little farther over that way. It's not really. The water's still there, and the water's always moving, but the crust down below is what's shifting slowly but surely, and that is an average speed for the last 30 million years. So that should give you a basic idea of how scientists have developed this theory of plate tectonics and some of the evidence that they used to build that theory, especially down under the ocean. What was the biggest earthquake? I was just going to say, we'll do some questions here. I always have to look this one up so I get it correct, but I've got it right here. The biggest one was the Valdivia earthquake in Chile. That was 1960, 9.5 on the Richter scale. The second biggest was the Great Alaska earthquake in 1964, 9.2 on the Richter scale. And that was right here in our area, created huge amounts of devastation. In our local area, the biggest problem was tsunamis. Remember, I am standing like almost on the ocean where I am right now, and the whole edge of our town was just completely wiped out by the tsunamis mostly. Even though the shaking itself went on for 4.5 minutes as that toe of that convergent boundary pushed out into the ocean, like we showed with that model earlier. The major destruction was because of the tsunamis in all the coastal areas around here. There's a lot of towns along those areas, and we suffered a lot of damage as a result of that. Can mountains turn into volcanoes? I would imagine the answer is yes, but I would have to look that up. If you had a mountain that wasn't originally volcanic, but became volcanic later, I don't know. That's a great question.
It is a great question.
That it could be.
Yeah.
Yeah.
So, Ed, does anyone have more questions for Darren? Because I think that some of our questions will be answered when we meet with Brandon on Thursday when he talks about the volcanoes in Guatemala. And he'll be showing you some
Nice.
lava flows and some erupting volcanoes. So it's good to have the science behind it and understanding why these humongous natural disasters happen. Um, and that whole theory of
See,
the tectonic plates is fabulous. And Sigrid says, thanks for the awesome presentation. And yes, Sigrid,
you're welcome.
this is cool. Okay. Uh,
um,
this is one of the
I
best
just wanted to show
presentations.
you.
Oh, go ahead.
Sorry. These will be pictures of Redoubt Volcano, which is close to us here, and it erupted back in 2009, 11 years ago. It was something we could kind of see from where we are, but not really. Can't actually see the mountain from here, but if we just take a 1.5-hour drive from here, then we can see that mountain very clearly. But you can see here in Alaska, these mountains will be a little different from what you'll see when you study volcanoes in Guatemala. Ours are covered in ice and glaciers. And so the dark areas are often areas where there's been lava or ash or mud. So here's what Redoubt looked like when it was erupting. There were some lava flows, but the main thing that we could see was these ash clouds coming out. And you can see where the ash has been deposited on the ice and snow. It's really obvious, all this dark. This was in March of 2009 that it erupted. This was early April 2009 when this picture was taken. So there had been a lot of ash already deposited on there. And if you look at this picture, this was taken from a satellite. So you can see the curvature of the Earth along there. And that dark spot there is the ash cloud coming from Mount Redoubt. So in space, it looked that big. It went tens of thousands of feet into the air. Huge ash flow, or ash cloud. And the ash was deposited, and then it snowed, and then ash, and then snow. And so you could see these layers of ash fall in between layers of snowfall, and they could actually see how much ash was falling and when, based on these little layers that built up in the snowfall too. Oh, I see an interesting question about a tsunami. What's a tsunami like? Like a tidal wave or oceans flooding the land? A tidal wave is kind of a, we'd call it a misnomer. It's not really appropriately named. It doesn't necessarily have to do with the tide. Although if it's high tide already, then the level of the water is higher up, and so the tsunami might reach farther onto the land. What happens with a tsunami is often there is a wave that's approaching the land very rapidly from out at sea, and it might only be a kind of a very low wave out in the ocean, but it's moving so fast when it gets closer, it builds up to quite a substantial thing. And as that energy approaches the land, the water will often pull away, and then it just sort of quickly floods the land. It doesn't necessarily come as a big breaking wave, although it could, depending on the shape of the ground. It's often just a big rush of water as that water floods onto the land, but it will go much, much, much higher than water normally would with any kind of normal wave action. So it's more of sort of a sudden surge of water up onto the shoreline. Think of in your bathtub, if you push your hand down at one end of your bathtub, it creates a wave. That wave will travel all the way to the end of the bathtub, and then at the other end, your little rubber ducky that had no idea what was going on is suddenly pushed up against the wall of the bathtub from this wave that came from far away. And so the movement of that rubber ducky might indicate that. And if the end of your bathtub were really shallow, that water, that wave would slide way up onto the land. So it really depends a lot on the shape of the land itself. And so nowadays we have tsunami warnings occasionally when there's a strong earthquake. They want everybody to just get away from the water. There are signs all over town that look like, hold on. lines that look like this. Because we have a lot of visitors from outside of Alaska. They don't necessarily know what to do if there's an earthquake. And it basically says, go uphill. As soon as you feel a strong earthquake, just get away from the water as quickly as possible. And that's really important because you can't necessarily tell when they might happen. Now, if we have a big earthquake, often the sirens will go off around town, and then we have a huge speaker that'll say, a tsunami warning has been activated. Get away from the coastline. And then you'll go to the radio and listen in. They might have an estimate of when a tsunami could arrive, which is great to know, but they can't say if it's actually going to happen. So we sit there and we wait, and the last several times that it's happened, nothing really much has happened. But it's better to be safe, hunker down up at the school or another safe location, listening to the radio at 4 o'clock in the morning, wondering what might happen, than to be down by the coast and have the water suddenly rush up onto the land. There is no warning necessarily that gives you enough time to get away. So our plan here at the Sea Life Center, if it shakes strong enough that I can't stand up, as soon as the shaking stops, we run up the mountain as quickly as we can.
Well, always good to be prepared, but thank you so much, Darren. This is always a great science lesson in tectonic plates and convergent and divergent, and it's just amazing. So thank you for sharing that with us, and maybe the students can look up some experiments, and all the resources are on the resource page at Connected North at Home.
Fantastic.
The students can look at that too.
Very cool. Well, thank you very much. One of the things that I like best about this is the idea that it's something that happens over millions of years. So none of us will ever actually see it happen. But to be able to explore the evidence that scientists have used to interpret that is really neat to me.
And just one last question. Owen wants to know what happens with the animals in a tsunami.
Oh, here at the Sea Life Center, the last time we had a tsunami warning, the only animal that was evacuated was a little sea otter pup that we had in the rescue program, which will make Mally happy. They basically just put it into a dog kennel, put it into someone's car, and drove it up the hill. But most of the animals, we just kind of leave them in lockdown. They're okay where they are, but human life is the most important thing, so we have to make sure that people are safe. And animals like, say, the birds, it would take way too long to try to catch them and get them somewhere else. So I don't know the specific plans, whatever they have, but if it's an immediate, urgent evacuation, the animals will unfortunately be left behind. Of course, if a tsunami just wiped out the whole place, some of those animals would probably survive in the ocean. That's where they belong. But I'm sure some of them would be lost to that. It's hard to know, but we do have to preserve human life first and try to keep everyone safe.
And we just try and keep everyone safe. So thanks, guys, and we'll see Darren again for sure. I'm not sure what we have coming up, but I'm sure that I know we have some things coming up with Darren. We love learning about the animals and the conservation efforts and all of the amazing things. And I think we want to look at another squid dissection. So we will see the students in about half an hour for nocturnal animals with Lannis, which are the animals that are awake at night, which is super, super cool. So guys, we'll see you soon. And thanks, Darren, as always, and be safe. We'll talk to you later.
All right.
Thanks, Darren.
Bye-bye. Thanks a lot.